In this lesson, we're going to consider how to take a part that has been loaded and find out what the stresses are along the length of a part. So up to this point, we've considered stresses and we've considered loading conditions, and now we're going to tie those two concepts together. So first we need to ask the question, how many ways can we stress a part? And that's going to be the discussion for the day. We're going to consider axial stresses. So this is where you take maybe a beam and try to pull it apart. You have shear stresses, where you're trying to cut it. You have bearing stresses, we'll discuss that. Torsional, twisting it, bending it. And so let's jump into the discussion. If we have an axial tension, so for instance, let's say we have a bar, and we're going to call the x-axis the long axis, here, and we apply some P and put this bar in tension. Let's make a couple assumptions. If the only applied forces are in pure tension, so there is no other force except for P here, and the forces are collinear in the x-axis, and they're applied through the centroid. In other words, it's important to note that P is attached right at the centroid of this bar, and we're only going to consider stuff that happens some distance away from the attachment point. In other words, there's some weird things that happen right here at the attachment. We're not going to consider that. We're going to drop down into the middle of the beam and consider what happens. If that's the case, then we can say that the stress is uniform across that cross-sectional area, and the stress is equal to the load we put on it divided by the area. So force over area. Okay. And any cross-sectional element that we make will have that distribution. In other words, this little infinitesimal spot has the same load as this one, which has the same load as this one, and all the way into the page across the cross-section. As long as we stay relatively far enough away from the end to handle any kind of weird conditions as the force is being distributed to the load. If we were to do a Moore's circle for this loading condition, it would look like this. This has all three circles because sigma 2 and sigma 3 are equal to 0. Shear does exist in this stress state, but only indirectly. So we've got the stress that we're creating, this P over A, is the principal stress that's occurring within the part. Okay. Considering direct shear, and we need to be very careful, we're saying direct shear occurs when there is no bending. So if you notice, there's a gap here, and it allows there to be a little bit of a cantilever beam, whereas in this one we're assuming no gap. We're not considering right now shear with bending, only pure shear. This is fairly hard to produce in real life, but if you find a case where this has happened in real life, the equation for the shear stress is just the force that you're using to shear divided by the shear area. So this formula is almost identical to the previous one, except for instead of a normal stress, we're producing a shear stress. Okay, the area of shear is the cross-sectional area of where the shear is occurring. Notice that's only going to be happening at this very small spot where the shear is trying to happen. There's no shear going on out here anywhere else. But it does occur equally for all points on that cross-sectional shear face. Okay, so that's shear. For bearing stress is what happens when you pin something together. That's the most common case for it to happen. It's compressive, so what we're trying to do now is squash this piece of material. So here's two pieces that have a pin running through them, and the formula is the force that we're using to try to pull these parts are divided by the area of the bearing. And here's the bearing area described up here. So let's see. The bearing area is going to be the diameter of the pin, the inside diameter going through, multiplied by the length of the pin, which in this case is the length of W and the length of G together. Okay. Turns out if there is a clearance between the hole and the pin, so if this pin is not a tight fit, then you also need to multiply this equation by pi over 4. That's a very experiential number of how we got that. So here's a case where there's double shear, and the question here, why is double shear preferred? And the answer is the single shear also produces a bending moment around those two bars, whereas the double shear is now allowing it to just be direct bearing and not anything else. So whenever possible, you want to have some sort of clevis with two prongs instead of just one. So the problem with direct bearing, the way it fails, is something called tear out, and tear out is when the material around the hole tears away. Okay, so if we look at the area of the link, this is where the bearing is happening on the link. It's down here at this bottom face. If you look at the clevis, it's these two faces here. If you pull hard enough so that tear out occurs, what's going to happen is the link, a piece of the link will come apart, and two pieces of clevis will come apart, and that's going to be how it fails. And so you'll have this big tear out area. The tear out area is going to be equal to 2 times L times T. So that's how the area is calculated. But for this class, we're going to just go ahead and go straight to the answer. And the answer is, or maybe I should say, before we can give you the answer, you have to know the question. The question is, what do we need to do to make sure we don't have tear out? And the answer to that question is, make sure that this value for L is always greater than this value for D. And if you'll do that for most cases, that's a good enough analysis to ensure that you won't have tear out failure. Okay, so now we've talked about axial, we've talked about pure shear, and we've talked about bearing stresses. The next two that we're going to talk about, torsional and bending, have something to do with moments. So before we discuss that, let's just take a minute to review what moments are. Here are the definitions for this class about and the notation that we'll use for this class for moments. So notice there are 3 things that we regularly refer to as moments in engineering sciences. The first one we're going to consider is a resistance to bending. It's the second moment of area, and it resists bending. So if you notice, there's a stress equation that has something to do with a bending moment in it. We'll discuss that in just a minute. Okay, so there's the formula. It's the integral of y squared dA. Then we have a resistance for twisting. So that looks like it has something to do with torsion. The equation has a T in it, standing for torsion, when we load things in torsion. And this one is the integral of r squared dA. Notice those two are fairly similar. They're going to have the same units, and they're really kind of accomplishing the same thing, just in different directions. One of them is resisting bending, the other is resisting torsion. The third one is the one that most people get confused with. This is a massed moment. It's a little bit less clear to describe what it's doing, but the best way to think about it is its resistance to angular acceleration. Matter of fact, in both of these equations, you can see that I is in the denominator. So the bigger I is, the more resistance the material has to a moment, and the more resistance it has to torsion. Also, the larger I is in this bottom, the more resistance an element or a part has to torques and to be accelerated. So this I would also be in the denominator. So this is a resistance to angular acceleration. It does not have the same units as the other two. It's a very different item. And we will not really consider I as much. It has something to do with mass, and both of the others have something to do with area. So I just wanted to make that clear before we go on. And also I want to point out that there is a relationship between the polar moment of area and the second moment of area. So there's the relationship between the two. Okay, so with that said, now let's take a look at a simple torsion analysis. So again, let's start with assuming some things, that the element that we're considering is not terribly near the applied loads or any kind of external constraints. Okay, so this is in the center again, that we're only producing pure torsion, and that pure torsion is exactly normal to the axis of the bar or part that we're looking at. And we're going to assume that the cross-sectional areas of the bar remain in the plane and also remain perpendicular to the axis. So in other words, we haven't moved it a whole lot, and we're definitely not twisting it out of plane or anything like that. And we also need to assume that the material is homogeneous, that it's isentropic, and that it obeys Hooke's laws, and that we're not actually bending the bar, and that the bar is initially straight. So if we can make all of those assumptions, granted not very many of them are trivial assumptions to make, but if we can make all of them, and also that the uniform circular area, the cross-sectional area is uniform as you move across that bar, then we can do a real simple torsion analysis, and we say we apply some theta, or we apply some torque, it produces some theta at a length L away from a cantilevered beam. And a couple things are important here. First off, we're going to be producing shear stress, not normal stress, and the shear stress is going to be maximum on the outside rim of the part. Okay. So a couple definitions, we'll call L the length of the bar, we'll call G the shear modulus, J is the polar area moment of inertia that we just discussed, and rho is anything from 0 to r. It's any particular radius within it. And so we can derive that this value of shear stress is equal to the torque we applied times the distance away the element is from the center divided by J. So the maximum obviously is going to occur where rho is maximum, which is the outside edge. And so that's why I said that it's the rim that has the highest stress. Notice I'm not putting tau xy because this is tau xy is occurring here, tau xz is occurring this direction, and anywhere in between is some combination of the two. So I'm going to drop the xy convention because the shear stress is not necessarily in the xy or xc plane at any given spot. We also can calculate the amount of deflection. So if I know the torque and I know what its shear modulus is and something about the area of the material and the length of the beam, I can actually calculate how far it deflected at a given torque. Okay. And a couple other things, if we look at a round hollow bar, J is known to be this, the diameter of the outside to the fourth minus the diameter of the inside to the fourth over 32, so I can plug that in for J. Obviously, if the inside diameter goes to 0, this term disappears, and so for a solid circle, J becomes pi d to the fourth over 32. It's probably something you should memorize. So what happens if this section is not circular? It's not as easy to calculate, but at the end of the day, some equations have been produced that say that the maximum shear is again occurring somewhere on the outside edge, and it's going to have the value of T over Q, where Q is equal to this formula. These are a couple out of the machine design, Norton's machine design book. So feel free to look back at table 4.3. There are others besides just a solid square and a hollow square. I wanted to point out that you don't necessarily need to solve the integration. It's already been done for us, and most of the time what we actually care about is the maximum shear and not a formula to tell us what the entire shear is everywhere. Okay, so now we've talked about torsion. Let's move now to a straight beam that has pure bending. Let's talk about what we're assuming. The segment again is analyzed a little bit away from the applied loads. The beam is loaded in a plane of symmetry. When we put a moment on it, we're putting a moment on in a plane of symmetry. The cross-sectional sections remain in plane perpendicular to the neutral axis. In other words, we're not deflecting it too far. Again, the material is homogeneous, and again, the material has to obey Hooke's law. And again, the stresses are not stressed so far that it goes above the elastic limit, and we're going to make sure that deflections stay relatively small. We're going to assume for the moment that the segment has pure bending, so there are no axial and no shear loads. Again, this is almost impossible to achieve in real life, but it gives us a place to start. And then finally, we need to assume that the beam is initially straight before we put a moment on it. So here's a way that we could possibly create that situation. We do have shear located on it, on the beam, but on the section between A and B, the shear diagram is going to be equal to 0, and there will only be an applied moment for that interior section. We'll look at it in just a second. So here's the shear diagram. Notice between A and B, these locations are in pure bending. So there's a moment diagram. And in this particular case, it's a constant moment for that entire section there in the middle of the beam. So let's take a look at what's happening in that section. When it's unloaded, it's initially straight. When it's loaded, there's some sort of deflection that occurs. And one of the key pieces to note is that the maximum compression occurs at the top and the maximum tension occurs at the bottom. Or another way to say it, the maximum stress caused by the moment occurs at the furthest distance away from the neutral or the centroidal axis. So the worst cases are up here at the top and up here at the bottom. Okay. The formula is sigma x is equal to minus myi. So now we've decided to take y from the neutral axis. So as y is positive, sigma is negative. As y is negative, sigma is positive. We're multiplying by the moment, and we're dividing by the second moment of area. Now the maximum is going to occur when we're at the furthest distance away. That's the c value. So we could go ahead and plug in and just figure out what the maximum normal stress is. It's going to be mc over I, where c is the distance from the neutral axis to the furthest point out. So compressive is negative, tension is positive, and c is not necessarily half the thickness. In this case, the centroidal axis runs right through the middle of the part because the part is symmetric about the axis, but that's not necessarily the case, and we'll do some examples of needing to calculate I and also needing to calculate C. Okay, so the last section of things we're going to talk about is now to say, well, what happens if there is bending and moment happening at the same time? So consider this loading diagram. Now there will be both shear and moment at the same location. And let's take a look. There's our shear diagram. So there is, at this particular location A, there is a shear force, and there is a moment force that's occurring at the same location. So let's take a look now, and we're going to spend some time looking at this particular diagram because this is very instructive for understanding what's happening with the shear forces at that location that we're considering. So first, let's just talk about what it is we're looking at. We're looking at a small section of the beam, so this is the x-axis moving along the bottom here. Okay. If we look at the thickness, it has a thickness of b, and we're going to be considering some small section that has a dx length along the beam, but has the full b length along the cross section. And it also has some height that's going to be equal to c minus y1. And what we're going to be doing is looking at different y1s to see what the shear stress is at this location. So what I'm really interested in is this B1, B2 plane here. It's this plane right here, which corresponds to this plane right here. That's what I'm interested in understanding. I know that there needs to be some shear stress, and what we're going to do is we're going to derive what that ought to be based off of what we understand is happening within the part. Okay? So a couple things to note. There's no shear stress on this bottom face. There's no internal stresses on the outside of the part. So with that said, let's look at a couple things. The element has a thickness B, right here, and it has a height of c minus y1, and it has a length of dx. The moment is increasing as we go from x on this side to x plus dx on this side. We'll call this front face x1, the second face x2, and the moment has increased from m to m plus dm. So there's a little bit of a moment that occurred in that dx as we moved across. Okay. We know that the shear on the surface is equal to 0. So if I want to find out what the force at any small element on B1 to C1, any place on this face, it would be equal to sigma dA. And we've just looked at what that would look like. That's my over I dA. And in this case, for a rectangular beam, the dA is going to be equal to B, that's going into the page, times dy. That's the small element of height at that location. Okay. So the total force on this entire face right here, the B1, C1 face right here, is going to be, we're going to find that by integrating the stress along each of those elements as we move along, and this is what that's going to be equal to. The integral from y1 to c of my over I times dA. Okay. Repeating the same process for this other face on the back side now. The only difference is now it's m plus dm, because that's what the moment is on this back side of the face. And then finally, we know that the total shear force on the face, B1, B2, is going to be equal to tau B dx. Okay? So recognizing that that's the case, now we can sum moments on this element. So sum of the moments in the x direction are equal to 0. So what that looks like is fx plus fxy is equal to fx, this should say 2, fx2 on this on x2 location. Taking a look at that, now plugging in what we just solved for last time, there's the definition of fxy. We subtracted fx from both sides of the equation, so there's the fx term, and fx1 term, there's the fx2 term. If you notice, they both have a my over I on integrating from y1 to c, so we can cancel those terms out. And now solving for tau, I'm going to divide by b dx, and I also can move the dm out of the integral. We're going to assume that the change in moment has nothing to do with the area. And so we get this dm over x times 1 over ib times the integral from y1 to c of y over I dA. That's the definition of the shear stress that's occurring at face B1, B2. And this is what we were looking for. A couple things to note. What is the derivative of the moment function? The derivative of the moment function is the shear function. So this dm over dx can be replaced with v. And so the problem reduces to this, v over ib. And the last thing is, for a given geometry, we could probably calculate what the integral from y1 to c of y dA is. That has everything to do with geometry and nothing to do with the loading conditions. So let's just define q as that integral, and that way we can maybe have a table of q's for different types of geometries. So that's going to give us a final working equation for the shear stress at a given location. It's a function of the shear force of that location. So let's calculate Q. So there's our definition for what Q ought to be. Turns out for rectangular beams, Q is found to be this equation, and the important thing that comes out of this equation is the maximum shear stress reduces to 3/2 V over A. So this is, if I want to know what the maximum shear is occurring on a particular rectangular beam, all I need to know is the shear stress that's occurring on the beam and the cross-sectional area of that beam, and I can know what the maximum shear stress is. For round beams, we've got a different tau max. It turns out to be 4/3 V over A. Okay, and now let's take a look just real quick at these equations. What happens to tau at the edge of the beam? So when R becomes closer and closer to Y1, this term becomes 1 and the tau goes to 0. Same thing for here as Y1 approaches half of the height. So this, if this is h over 2 squared will be h squared over 4. This top term will also go to 0. So what that means is my distribution, the maximum shear stress occurs on the neutral axis and goes to 0 on the edge of the beam. Okay, both for a rectangular beam and for a solid round beam. Now that's really interesting because the moment was the exact opposite. The moment had a maximum stress on the outside and went to 0 at the middle. That's turned out to be really convenient for us. That means if a beam has moment and shear forces acting on it at the same time, the worst effect of the shear happens on the neutral axis, whereas the worst effect of the moment happens on the surface of the material. Also, if you consider that, so moments contribute to normal stresses, shear forces contribute to shear stresses, and the moment is the integration of the shear. So the longer the beam is relative to its depth, the more M is going to dominate, because we're integrating along dx as we move along. So what that means for us practically is if the beam is practically longer, 10 times longer than it is thick, we don't really even need to consider the effect of shear. So although it's very unlikely to find beams in practice that are loaded in pure moment, in practice a lot of beams are 10 times longer than they are thick. Since the beams are so much longer than they are thick, we can understand that the moment is going to be the driving force of the maximum stress inside the part, and we don't even need to consider what the shear forces are contributing. So, a couple other things that are useful. The maximum shear stress for hollow beams is roughly equal to 2V over A, and for I-beams it's roughly equal to V over the area of the web, and the area of the web, just so we're all consistent, is going to be the area of this inside section, not the outside section. So if I'm trying to find the area of the web, I'll take this small length right here, multiply this length here, that's going to provide the area of the web. Alright, so let's summarize today's discussion. This table shows basically what we've talked about. We have loading in the axial direction, and we have a formula for what that looks like, and we understand that its distribution is everywhere across the area. Pure shear, it's also across the entire area, and there's our formula. For bearing, we actually didn't derive any formulas. All we said is make sure that the length to the hole is greater than or equal to the diameter of the hole, and we don't need to worry about whether bearing tear out is going to occur. For torsion, the maximum torsion occurs on the rim of the part and follows the equation TR over J. For pure bending, the maximum occurs at the furthest distance from the neutral axis, in tension and in compression, and the formula is MC over I. For transverse shear, the maximum occurs again on the central axis now, and it's going to, the official formula is VQ over IB, but for a rectangle it's going to be 3V over 2A, and for a round it'll be 4V over 3A, and again, and here's the picture of the way that stress occurs. We'll be talking some in class about how to solve some of these problems and start doing some combined loading. So this is our first introduction this semester to the way parts are stressed as we load them.